This is a lecture on misalignment detection. Like we had in the last class discussed about unbalanced detection and how balancing can be done to prevent unbalances. But if you look at mechanical systems, there are many types of mechanical faults which can happen. One of course is unbalance, which we had discussed, and the next most serious is the occurrence of misalignment between two shafts. And of course, there are related defect to misalignment like eccentricity of the rotor, shaft being bent or bowed, and maybe cocked rotor. So, and then because of misalignment or why things become loose, what happens if the foundation has become loose or what we know as soft foot foundation. So, how this occurs in machines is what we are going to discuss in this class, and then what are the methods to detect them, and then also tell about some things about how we can reduce the occurrence of misalignment etc. in a system. So, if I was to talk about misalignment, essentially in any plant, as you know, basically we have two systems. One is the prime mover and other is the mechanical unit or the driven unit. Okay. This is the prime mover and this is the driven unit, and this is the coupling. And most important point here is the center line of the shafts. So, basically this dashed red line is the shaft center lines between the prime mover and the driven unit, and they have to be in one same straight line horizontal to the ground. If you look in the vertical plane or if you look in the side view, this should make one projection. Okay. Now, if this does not happen, how do we maintain this? This coupling basically brings about the two shafts together. Basically, these two shafts are brought together by this coupling, because I have exaggerated it, and then they are bolted, the parts of the coupling are bolted and then the shafts are held together. So, if this is not held together, we will have certain problems. Okay. I will come to a description as to in the laboratory how we have discussed misalignment, but before that there are two serious types of misalignment which can occur in the shaft systems. Suppose I say this is shaft A and shaft B. By misalignment, I mean that shaft A and shaft B and this is the end of the coupling, okay, face of the coupling. This is one scenario wherein this shaft is offset, the axes are offset, and this is known as to be, and but they are parallel. Okay. This amount of offset could be about 2 to 10 microns or more, depends on the speed of the machine. In fact, there is a standard which specifies for a rotational speed the maximum amount of misalignment, and these are available in handbooks. So, if it is a 500 RPM, this will have a certain value. If it is 1500 RPM, it will be some other value, and so on. So, in one case we have what is known as the parallel or offset misalignment. In another case, we have the shafts at an angle to each other. Okay. Some theta shaft A, shaft B. So, this is what is known as the angular misalignment. So, we have the parallel or offset misalignment and the angular misalignment. Okay. So, what happens in such a case is this will give rise to certain forces in the bearings, because as you know, the shaft systems are supported on bearings. If my coupling, they are supported on bearings. Okay. If they are misaligned, either angular or offset, they give rise to additional forces and moments, okay, at the bearings. So, we will have a failure of the bearings because of misalignment, and then we notice a defect because there will be excessive vibrations at the bearings. But when there is excessive vibration of the bearings, people are misled that they will say that the bearing is at a fault. But the problem is the misalignment created a fault in the bearing, or in the previous case like we had seen, unbalances which went undetected created a problem at the bearings by giving in excessive loads or fatigue loads at the bearings. So, bearings are going to fail. So, to monitor a misalignment, we need to look into certain special characteristics of misalignment, which I will discuss later on in this class. But usually people in the industry are alarmed by having excessive vibrations of the bearing, and everywhere, and that is a problem we will face while doing CBM, because we do vibration monitoring or measurements at the bearing locations. Invariably, people will always say that the bearing is at fault because bearing is vibrating excessively. That is the, and then if this went unnoticed, the bearings would fail, and then people will say the bearings failed, so my machine failed. But actually the reasons could be something else. Reasons could be like the misalignment which went unnoticed, which was not corrected, gave rise to this kind of an excessive force in the bearing, and then the bearing failed, or unbalance which went undetected gave rise to excessive forces on the bearings, and bearings failed. So, to diagnose or detect faults in misalignment, we need certain special vibration monitoring or signature analysis, and the typical characteristics of misalignments are something which you will see in the vibration spectrum or spectra measured at the bearing locations. Invariably when a shaft is rotating at, you will have a vibration at 1x, okay, but there will be some other components at other frequencies like 2x, 3x, 4x and so on. When you see high levels of harmonics or an excessive vibration in a particular direction, we may be sure that this is misalignment. So, let me tell you what we did to study the misalignment in the laboratory. Okay. This is the setup which we are using in the laboratory, and in fact, we will be using this setup to demonstrate other defects like the eccentricity, like the bent shaft, the rubbing in the shaft, the cocked rotor, etc. Basically, here you will see this is a motor, which is my prime mover in this case, and this rotor on a shaft supported at two bearings. You see one bearing here and another bearing here, which is my system, and this black one is the coupling. Okay. So, to introduce misalignment, we have this dials here which could be turned around, and this system could be loosened, and so that we can push either both of them away and create an offset misalignment, or if I just push one of them by holding one constant, then I can create an angular misalignment. Basically, to explain it to you again, if you look at the top view of the system, this is the top view. This is my motor, this is the coupling, this is the drive end bearing, this is the non-drive end bearing, and this is the yellow rotor. So, in fact, you will see this two white dials here. Okay. This dials, this one dial here and another dial here. So, these two white dials, they could be turned. Okay. And then I can force this, move it, so that I will create an angular misalignment. And if I move or if I move both of them, I can create a parallel misalignment. Okay. Now, to measure the vibrations, I can measure at each of these bearing locations in x, y and z directions, and similarly here in x, y, z direction. Okay. So, these kind of vibration measurements can be done, and then basically this is my axial direction along the longitudinal axis. Y happens to be the horizontal. For clarity, I have just moved it here, this point, but this is actually at location A and location B. Okay. So, basically, I will have 6 measurements in location A, x, y, z, location B, x, y, z. I will have total 6. So, these kind of vibration measurements can be done in any machine. Okay. In this case, to notice the angular misalignment, we are not moving point A. Okay. Now, this misalignment, amount of misalignment does depend on the flexibility of the coupling, and that is very, very important. Couplings play a major role in the prevention of misalignment. You would have heard of this flexible coupling, rigid coupling, or the universal coupling. Okay. Basically, in flexible coupling, there are elastomer elements kept, which will take small amount of offsets can be accommodated. Okay. Rigid couplings do not allow per se any offsets. but then there are universal coupling wherein these angles could be as high as 7 to 10 degrees. Okay. A good example of universal coupling is what we know as Hooke's joint is in the automobile drive shaft, or sometimes it is known as the propeller shaft. They can take good amount of angular misalignment. Okay. So, the couplings play a major role to accommodate such parallel or offset or angular misalignment between the driver and the driven unit. Okay. But despite having these couplings, we will still see lot of forces and moments coming at the bearing locations. I mean, why at all misalignment is a serious issue in machinery? Because for the fact that misalignment will load the system. So, when I give a power to a machine to run it, I am unnecessarily wasting the energy to rotate a misaligned shaft. For rotating the same misaligned shaft and the perfectly normal not misaligned shaft, I will require less power to rotate the normal or perfectly okay shaft than compared to a misaligned shaft. So, I do not want to waste power, and the other effect is if misalignment goes unnoticed for a longer time, the forces and the moments occurring at the supports are going to increase, the bearings are eventually going to fail and large clearances may occur in the bearings, and then things will be loose and so on. So, once we are talking about misalignment, some of the related issues with the other mechanical defects are, let me list them down. Related mechanical defects. One is rotor eccentricity. Other is cocked rotor, bend or bored shaft, soft foot looseness. We are going to discuss about soft foot and looseness in few classes down the road. But the reason I wanted to tell you is, once we look into the vibration spectra, the signature of the defects like rotor eccentricity, cocked rotor, bent bore shaft are almost very similar at times. So, we should not be misled as to a misalignment has occurred. Okay. Though there are means by which misalignment can be detected and then separated out, but particularly at high speeds the behavior is almost similar, and then we should at least know what do we mean by a rotor eccentricity. For example, if I look at a rotor, by rotor eccentricity I mean the rotor's center of mass is not at its center of rotation. Another way to look at this is, maybe I should draw the figure the other way. I have a large disc, okay. This is my center of mass, but I am rotating it, the hole has been made here, and this is my center of rotation. So, you can understand the rotor is going to wobble and make an ellipse like thing. At some point, if I should draw it. Okay. So, this at some point I will have large forces, large displacement and less displacement. Okay. If this was a perfectly balanced and eccentric rotor, the displacements at locations like they are called, the 12 o'clock position, 3 o'clock position, 6 o'clock or 9 o'clock position will be same. Okay. But if they are eccentric or the center of rotation is not at this mass center, they will be wobbling and one level will be less compared to other, and here maybe another level, this is more compared to this. Okay. So, the displacements along the circumference are not same. Okay, and that is because of this eccentricity in the rotor. Okay. It is very easy to measure it. Okay, and there is an instrument, all of you would have been familiar, must have, it is a very common instrument in the lab, that is a dial indicator or a gauge. Basically, it is a spring loaded stylus. Okay. Spring inside it, and then we will have an indicator, which is either it could be 0 here, plus in this direction, minus in this directions. Okay. And this stylus will be contacting on a surface. If this surface is going to have a motion this way, it is going to swing in this direction. If it is going to have motion in this direction, it is going to swing the other directions. Okay. And these readouts are usually in micron. So, a dial indicator or a gauge can be put on a rotor which is rotating at these locations. This is basically the dial indicator. Okay. So, by knowing the measurements in the dial indicator at these 4 locations on the circumference, one can decide the amount of offset which has occurred, and usually these measurements are taken on the flange which is there, which is mounted on the shaft. If I have a shaft, because the shafts only meet at the coupling. Okay. If I was to align these 2 shafts A and B, whatever motion this is going to happen, this is also going to have the same motion. So, I can see the dial gauge reading here, I can see the dial gauge reading on this surface, and then as I rotate it, they should all get the same reading. Okay. If not, we will have to play around with the system, and that is how I will tell you. For example, in this system, we see that the level in this has increased, in particular in this direction. Okay. So, in fact, in all of these foundation, there are very thick steel plates which are known as shims. Shims are very hard, wear resistant, steel plates or inserts, which are introduced right at the time of installation, and then we put the foundation bolts. Okay. Similarly, so by adding or removing shims, adding or removing shims, this can be taken care of. And in this system, we had the provision of putting shims at these locations. If you look here, you can remove, this is the foundation of this bearing, and then shims could be introduced, okay, and then we can align them as to they are in perfect horizontal displacements. Okay. So, this kind of shimming is done right at the foundation by measuring the radial runouts, and these distances which we measure are known as the radial runouts. The radial runouts in the 12 o'clock position, 3 o'clock, 6 o'clock and 9 o'clock positions should be same. So, they are concentric, okay. And another relatively between shaft A and shaft B, they should be also same. And if they are not, we have to play around with the shims to adjust the level. Okay. Maybe this is only in the horizontal, in the vertical plane, you have to move something in the horizontal plane as well. Okay. For example, in the top view, I have shims here, I have shims here, I have shims here, I have shims here. If I add or remove in one plane, I can reduce the angular. You can understand if there are, this is at elevated locations, this location is elevated compared to this will be having a rotation like this. The base plane, it may be like this. Okay. And this gives rise to what is known as the angular misalignment. So, by adding or removing shims, I can take care of the misalignment by either reducing the radial runouts or in both in the angular sense or in the normal vertical or horizontal sense. So, what are the factors which affect the misalignment? Of course, one is the machine speed, because if the machine speed is high, the forces will be high and the misalignment could be there. Coupling stiffness plays a very important role in the misalignment. Okay. As you have seen, we allow a flexible coupling or a Hooke's coupling to accommodate certain misalignments which is required by our functionality. For example, in an automobile propeller shaft, the reason we give a Hooke's joint is because of the fact that if this is my wheel and engine is here. So, my output shaft is at a higher location than the driving shaft axis. So, to account for this kind of angular deviations, of course, we have to give rise to a coupling which can take care of, and that is what is done by actually the Hooke's joint or the universal joint. So, misalignments are sometimes required and sometimes they have to be of course reduced in a rigid machine, and that is where the coupling stiffness plays into account. So, that is why we have the flexible coupling. In a flexible coupling, if you look at the bolt holes, I am just drawing 4 bolt holes. In every bolt, there will be provision to have an elastomeric insert, okay, which can take little bit of radial play and reduce the amount of misalignment. These are there kept in the machines to take care of. Now, what are the effects of misalignment? So, additional forces and moments at the bearing locations, okay, and these forces can be calculated, okay, forces and moments. In this class on the preliminary condition based monitoring, I am not going to the details of how these forces and moments are derived, but out of our research work, these are there in the published paper, and you can visit this website of ours, iitnoise.com, wherein you can refer to the journal papers in the research section, and then see the papers on misalignment. Basically, this misalignment in systems which are carrying a normal shaft as to crack shaft, etc., how these forces and moments are computed, and why, because of the, if you look into the this is the x axis and the y axis, there will be deflections of delta x, delta y, and if you are looking at 3 dimension delta z. So, these deflections because of misalignment and the system already have stiffness. So, as you know, F is equal to K times delta x, F x, F y is a different K x, K y. So, these delta x, delta y, delta z are because of misalignment. The system has stiffness K x, K y, K z. So, we are going to get these additional forces F x, F y, F z, and of course, depending on the length, we will have a moment arm and this couple. So, additional forces and moments do happen at the bearing locations because of misalignment. Obviously, if additional forces are coming, they will oppose the system. So, once they oppose your load, we are going to have additional power consumption in the system, and then because of these forces are changing in direction at every rotation, they will induce fatigue load. So, the problem gets compounded. You see, a small delta x which has gone unnoticed will create a fatigue load, and because of fatigue, our systems are going to fail much earlier than they were designed or designed for. Okay. So, to avoid such fatigue failure because of misalignment, we have to ensure that this delta x, delta y, delta z are kept to a minimum. So, how can this minor alignments be mitigated? Of course, we just discussed about flexible couplings, and then we have the universal coupling, and in the industry, particularly when we have a lot of high torque and power being transmitted or converted, we have what is known as a gear coupling. Gear coupling allows for certain and linear movement of the shaft. For example, if you think of it, one gear sitting like this, okay, and another gear sitting on top of it. Okay. So, there will be a slight amount of movement is allowed. This is essential because of temperature, particularly in industries. We have the systems rotating almost round the clock 24/7. Okay. And of course, there is a amount of forced convection, or there are blowers in the motors, okay, which cool the bearings. But sometimes we have large gearboxes. The temperatures becomes very hot. So, there will be small amount of thermal expansion. Now, if the things were held rigidly, both the driven unit and the driver unit, they were held rigidly, and the shafts underwent a thermal expansion, and if there was no space or no allowance for this expansion to take care of by allowing a linear movement, they are going to bend, because of this shaft are going to bend or bow. So, to allow for such thermal expansions, usually gear couplings are used, which will once the thermal expansion happens, they will expand and then they will slide, and this could be few mils, very few microns, but nevertheless they are going to take care of this. Now, even before this is done, this happens later on when you are running the system, but once what happens when you are installing in the system, during installation, alignment has to be checked. And that is very important, and the traditional methods are by using dial indicators, what is known as the two-phase indicator method. Another is the reverse dial indicator method. Of course, these were the preferred method in the industry, wherein you measure the radial runouts in the 4 different locations, that is the 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock locations, and then try to estimate the average radial runout, and then try to use the SIMS either in the vertical plane or in the horizontal plane or across the 2 foundation axes as I discussed. And then another method is the reverse dial indicator method, which is very popular, but of late people are using what is known as the laser based alignment system. This is for the fact that, because in the previous first 2 examples, first 2 methods, two-phase or the reverse dial indicator, our meeting and the 2 shafts have to be very close to each other, so that we can take the dial gauge readings through a common shaft. But imagine the case of maybe a windmill, okay, where there is a long shaft, okay, and then we have this gearbox here, okay, and then alignment here, and then we have the fan here, and there is a coupling here. Okay. And this could be about 2 to 3 meters. So, how do you align such a system? Okay. And that is where lasers are helpful. Because lasers can travel straight line in straight line, and if I put a reflector, they are going to reflect back. Okay. So, imagine if I have two systems, this is one flange and another flange. So, one scenario. Second scenario is, and this is, okay. In first case, if I shoot a laser beam, okay, it is normally incident. So, it is going to reflect back. In this case, shoot a laser beam, it's not normal. So, if this is the normal, it is going to come out somewhere like this. Okay. So, if I have this is my laser transmitter is here, transmitter and receiver. Okay. I should see a single dot. Come on, this is going in and coming in. Another way, if I put a mirror here, okay, at some point I have exaggerated it, I will be getting 2 points. Okay. So, I can play around with the shims at this locations, so that I align it and then ping it back, so that they all boil down to 1 point. So, in one of the mirror planes, one is this dot and another is this dot. So, I have to play around, so that both the dots come together, both the dots come together. Okay. So, the laser alignments are very helpful in this regards, and particularly you would have seen that when you go to an automobile garage. Okay. The 4 wheels of the shaft of the vehicle have to be laser aligned. Okay. Basically, they use this laser based alignment systems also. They have a reflector, they have a mirror, and then they will make sure, and then here they can change the camber angle and the caster angle, and there are adjustment bolts wherein I can change the camber and caster angle to ensure that the wheels are aligned. So, the same laser technique laser band alignment system is very popular to do machinery alignments. Okay. Now, I will come to what is the best way to find out whether a misalignment has occurred in a system through vibration monitoring. Okay. In this, what we do, as I was telling you, we will measure at any location the axial, vertical and horizontal vibration locations. And if you will see, if you will go back to the equations of flexible coupling or the Hooke's coupling, Hooke's joint. Okay. If I have an input shaft N and if I put a Hooke's joint, the output shaft is actually a function of, if this is rotating at omega, this output this is the speed, the output shaft speeds will be proportional to cosine 2 omega. Okay. So, this 2 omega comes. So, if I am rotating at 1 x, because misalignment, I will have a strong vibration at its 2 x in the axial direction. So, this is the most important diagnostic indicator in a vibration spectrum. Whenever we have a misalignment, as opposed to the unbalance it was strongly radial, here it is high axial at 2 x frequency. If you recall, unbalance was high radial at 1 x frequency. But let me just caution you, this is very theoretical in the sense high axial at 2 x vibrations. When we go to the lab, we see 3 x, 5 x, sometimes we see even high radials, okay, when there is eccentricity with misalignment. So, one has to be careful. Though if you go to any handbooks on condition monitoring or any trade guidelines, they usually give a machinery troubleshooting chart, and which says we have to, if it is high axial and in 2 x frequencies, it is misalignment. That is well and good, but then one has to be careful that it is not necessarily always true. Okay. So, misalignment detection by vibration measurements. Generally, a high axial level of vibration compared to radial levels. Okay. Compared to radial levels, that is a good way to look at it in comparison with respect to radial levels. But sometimes exceptions are there at parallel misalignment and so on. And now, what I am going to show you is, this is a case wherein we had the vibrating machinery rotating at 30 hertz, okay, and then we had different amounts of misalignment. Of course, they were all measured in axial directions, and we will see usually 2 x and sometimes very close to this is a 3 x and 5 x is occurring. Okay. So, what I meant to say is always it is not right to say that always only 2 x will come, but this is characteristically different than the case of unbalance. In unbalance, we will very rarely see things beyond 1 x. Okay. Okay. Of course, another thing is we have to take care of the phase measurements. Phase measurements do help us. For example, I talked about the bent shaft. So, in a bearing, I have a shaft which has a rotor. Okay, and if there is an unbalanced mass, I will see the vibrations at bearing A and B are in phase. So, phi of A minus B is equal to almost 0 degree. This is case of unbalance. Okay, if the shaft was bent, I have in my drawing I am exaggerating this. Bend shaft. You will see when you have bend shaft, this will be close to about 180 degree. So, these are characteristics of the phase measurements or the characteristics of the vibration spectra when a misaligned case has occurred. Okay. So, to summarize, in this class on misalignment detection, we studied about how misalignment occurs and why sometimes we have to purposefully give misalignment, so that the thermal expansion between systems can take place, and that is why in the industry we have a lot of gear couplings. In the automobiles we have the hooks joints because of the large angular deviations between the engine drive shaft or the crankshaft and the propeller shaft of the vehicle. Sometimes we allow misalignments because of installation defects to few microns, and that can be accommodated by flexible couplings. Okay. But despite our best intentions of giving gear coupling, hooks joint, flexible coupling, the misalignment, as you have seen, will give rise to excessive forces or moments, and these forces and moments are time varying and they are periodic, and so they are going to induce fatigue loads at the bearings. So, bearings are eventually going to get subjected to excessive forces because of misalignment, and again because of misalignment, because these forces have come, we are unnecessarily using extra energy to overcome this resisting forces. So, the power consumption also increases because of misalignment. So, in an effect, this misalignment has detrimental effect into the machine health of the machine, which has to be avoided. To detect misalignment, basically at slow speeds we can turn around the systems, the shafts at the flange faces, and measure the radial runouts. The runouts should be the same in both the systems, that is the driven and the driving unit. If they are not, the runouts are not, we can play around by inserting shims at the foundation locations. So, that and then we can raise or lower the foundations as to the required amount of microns measured in the radial runouts, and once we have done that, we misalign the system. But for reasons unknown to us, misalignment does occur, it occurs in machine, and then the telltale sign to identify misalignment is to look into the 2x axial vibrations in the vibration spectra measured at the bearings, typically to distinguish themselves from unbalance. In unbalance, we have high radial at the 1x direction. Of course, when there is overhang rotors having unbalance, as we have seen, there could be also the axial components, but usually in the case of misalignment, it is the 2x axial direction of vibrations, which is very high. Okay. Thank you.